and welcome to episode number 8 of CS350 Online. I'm your host as always, Leslie, and in today's episode, we are going to wrap up our discussion of synchronization. In particular, we are going to be looking at some of the other sources where race conditions can appear. We've really focused so far on how race conditions are a result of you writing some code where you have multiple threads reading and writing a shared variable potentially at the same time. But what's really interesting is that race conditions, especially with modern architectures and modern compilers, can actually appear through no fault of your own. And we're going to talk about those. And then we're going to talk about one of the consequences or side effects that you can have with synchronization, and that is the problem of deadlock, and that will wrap up our lovely section on synchronization. All right, so just a reminder, some readings if you want to do them, they're not required, and lots of pthreads help online. We did actually have a help video last term for pthreads, and I'm going to see if I can dig it up. I didn't actually make this video, one of the other instructors did, so if I can find it, I will post it. But give me some time. All right. That's a bit better. Sorry, everything was kind of looking a little blue. Now everything looks red. I think my camera's having a bit of a hard time picking up on the color because now I seem to be cycling between blue and red, and that's interesting. Anyways, all right, let's look at our OS of the day. So today, we are talking about an operating system that I would not consider a success, actually. So this operating system is called OS 360, and yes, I mean, it sounds a lot like the one you're using right now. OS 360 is a very well-known operating system, especially if you know anything about computing history. It was produced by IBM, released in 1967 for their System 360 series of mainframes. And in fact, the Red Room in MC actually used to host one of these machines. And I know it's been a long time since you've actually been inside MC. And the Red Room, of course, doesn't even exist anymore. Part of the Red Room is actually still around, which is interesting. A lot of it's actually been turned into classrooms. But where it gets really interesting, is that the one area down on the first floor now hosts a big fancy data cruncher again, which I think is really cool. And if you've been in the first floor of MC in the last few years, there's actually a lot of pipes that are running around under this, actually visible in the ceiling, that are actually being used to cool this big computation beast downstairs, which is kind of cool. Question on Twitch, well known for being a failure or just well known? Well, it's well known. It is a bit of a failure, and I'll get to that as well. I mean, it's not that it didn't sell. It sold really well because the computer sold really well. Failure in the sense that when they set out to do some specific tasks, they didn't actually achieve them until many, many years after everybody else had actually achieved them. So OS 360 was released right around the time that other operating systems had already demonstrated the feasibility of wide-scale time sharing. So DTSS was being used at Dartmouth College, and they actually were able to do large-scale time sharing preemption. And this was released just around that same time. And originally, IBM wanted to offer 3 different levels of this operating system, depending on how much money you were willing to spend. So PCP, not to be confused with the drug, of course, was really meant for users who purchased the low memory system. So if you didn't have a lot of money and you bought the low memory system, then PCP was the OS you should choose. And this wasn't much more than a batch processor, maybe with a bit of multi-programming. And then there was MFT, and that one actually did support multi-programming, so the other one didn't. But MFT had multi-programming, but they could only support it for a fixed number of tasks. And then MVT was the most expensive variant, and that supported multi-programming with a variable number of tasks. Now keep in mind, multi-programming had been around much, much earlier, and in fact everybody else, or at least some of the other major operating systems, were already doing large-scale preemption and time sharing. So the truth is, IBM actually tried to, for their MVT version, they were actually attempting to implement time sharing preemption, so proper concurrency, but they failed. And they continued trying to get this to work for many, many years. And it wasn't until 1971's release of OS 360, yes, they kept releasing updates to it, that they actually managed to offer time sharing finally. But at this point in time, Unix exists and Multics exists, and they've had these functionalities for years. So IBM was really behind the times with offering this. Now, of course, for people who were locked into using the System 360, they would have had to have waited, because operating systems like Multics and Unix, even though Unix was designed to be quite portable, may not have actually been ported to System 360 at that time. I don't quite know. All right. So you might have thought then that in 1971 this became really popular because of time sharing, but it didn't. It did become popular for a short period of time, but that was actually due to the editor and the debugger they provided, not due to the time sharing, because again, other operating systems had been offering it for longer and more successfully. Now, this operating system continued development for some time, and later editions introduced this thing called vSAM, so Virtual Storage Access Method, which is actually how IBM's DB2 kind of got started. So their database systems got started from System 360 and the OS 360. Yeah, it's pretty cool. And I wish our school had actually kept the System 360 around. And I know at the time they were probably like, okay, we've got this big outdated mainframe. Why would anyone want it for historical reasons? Let's just get rid of it. So they got rid of most of it. But looking back, I'm wishing they had kept it, because I think it would have made a really interesting display around MC. I think they have one control board and a few other pieces of it, but I still think it would have been cool if they had kept the whole thing, so that you could actually like have this really cool display of where we have come from and where we are today. And I mean, this is one of the problems. A lot of the hardware from these eras doesn't even exist anymore, because people never thought that we'd want to look back and reflect at where we've actually come from. And if actually computing history really interests you, once we are actually allowed to leave our houses and travel again, and maybe if you ever get to go to Cali for real instead of, Cali over the internet, I really recommend you go to the Computer History Museum in Mountain View. It's actually a really cool place. It's not free anymore. I think it's like $20 or $25 now. It used to be free. But it is worth it, and they actually have a lot of this stuff that we talk about in these little segments, and they even have some of these things working. And I know when I was there last, they had a PDP-1 working, and you could actually play like some of the original games like Asteroids on it. And that was really cool. Playing Asteroids on a big phosphor screen where the image stays for a few seconds afterwards. So it's kind of like got these cool ghosty trails. It's really neat. It's really, really neat. All right. But I don't want to make you all sad, because I don't know when this, I think the lockdown is officially over, but I'm not sure. And then when do we actually able to open up and go places? I don't know. So there is a question on Twitch here, and then is a question about interrupts. If you spam your keyboard and mouse enough, can you theoretically block any other interrupts from doing work, since you keep forcing a context switch? It is possible, yes. I don't really feel like it's been possible for a long time. So I don't think we as humans are actually capable of doing this anymore. But I remember in the 90s, you could actually spam, like you could push the keyboard buttons fast enough. It was mechanical keyboards back then. Like my keyboard I had in the early 90s was 8 pounds of steel. 8-pound keyboard, yes. Your laptop weighs less than half of that. I had this 8-pound steel keyboard, and it was a mechanical keyboard. But you could actually push the keys fast enough on it that a lot of the key presses would actually get lost, because the interrupts, they just weren't being handled. I don't know so much if that's possible to do that anymore, but it definitely was. I mean, nowadays this we actually have a queue on the CPU, and it can only queue a few interrupts, but also devices tend to repeatedly fire interrupts until you actually acknowledge their completion. We'll talk about that another time. And for the person saying, the more clicky the keys, the better, I totally understand. Unfortunately, that 8-pound keyboard I ended up getting rid of because it wasn't the current key. It wasn't even compatible with the current keyboard spec. It was so old that you would actually have to get like a Raspberry Pi board and like do a little hardware work to get it to work with a modern computer. So I gave it away, unfortunately. But it was the ultimate in clicky. It actually had like physical springs. And I mean, it was 8 pounds of steel. It was a monster. Yeah. All right. So another question on Twitch is that why sometimes spam clicking makes a frozen computer wake up? I don't know. So to be honest with you, this concept of going into hibernation or sleep mode, we've had this concept in laptops and computers for a really long time, but in my opinion, it doesn't work that well still. So, I mean, it's gotten a lot better. Like, I remember in the 90s, this concept of putting your computer into sleep or hibernate mode, it was almost impossible to get it actually out of it and have it actually work properly afterwards. And then in the early 2000s, they started getting better and better. Like, Windows got reasonably good at it, and I didn't own an Apple computer until about 8 years ago, so I can't comment on them. Linux-based operating systems were really awful at the sleep and hibernate. They're a lot better now, but they're still not perfect. And the same with Windows. Now, Apple tends to handle it the best, the getting out of sleep and hibernate. But even still, it's not perfect. I know yesterday I actually had to reboot it, like physically power it off in order to get it to come out of sleep mode. So, yeah, they're not perfect. Comes down to implementation and architecture details. All right, so that's enough distractions. Clicky keyboards. The one thing I will say about clicky keyboards is they're absolutely amazing to type on. Nobody would ever argue, but they tend to annoy everybody else in the room. Although, the laptop I'm planning on buying to replace this Apple has a mechanical keyboard, so that should be fun. Although surprisingly, the Apple keyboard is pretty loud, I find. All right. So where do we leave off then? Enough talking about all this fun stuff. So we left off, we were talking about condition variables. So condition variables, remember, that is this magical synchronization primitive where we are in a critical section protected by a lock or some kind of mutex, and the shared variable that we need to have a particular variable that's being protected by the mutex doesn't have the value we want it to have. So we can't continue on in the critical section because the variable has the wrong value. And at the same time, nobody else can actually change the value because we own the lock. Oops. And that's what a condition variable is going to let us do, is it lets us simultaneously fall asleep while releasing the lock so that another thread can acquire the lock, change the value of the variable, and thus changing the condition so that they can wake us back up. And when we wake back up, we simultaneously do the wake up and reacquire the lock. So that as far as we are concerned, whenever we are actually executing code, we actually own the lock and it is safe for us to modify or read and write that shared variable. So we used condition variables for that. I showed you a few different ways you can simulate the behavior of a condition variable using locks in a loop. And you can see that it's not... where is it here? So this is one of the ways that you can actually simulate the behavior of a condition variable with just a lock. The problem, of course, here is that we're actually busy waiting. So instead of waiting for the condition to become true by actually going asleep and not, wasting the CPU's time, we're going to sit here and we're going to poll. And that's not what we want to do because that's going to be useless cycles. And when you're talking about writing efficient programs, one of the things you have to be aware of is, am I doing something that's not actually making progress in the program? And if I sit here and I spin asking the same question over and over again, I'm not making good use of my CPU's time. And so this, while it technically works, is wasting the CPU's time and resources. And we don't want to do that. So that's our condition variable. Even though we still have this loop here, instead of repeatedly spinning, we're actually going to be blocked and asleep until the condition is actually met. And the whole reason why we actually need the while loop is because when we wake up, we don't immediately run. We go to the back of the ready queue, and if we go to the back of the ready queue, then the problem is some other thread could get scheduled to go before us and change the condition back again. So we need to make sure that when we do run, that the condition hasn't changed back. But the bulk of the waiting is not done by spinning. The waiting is actually happening by sleeping, which means that other threads can actually use the CPU in a meaningful way. All right. So then we also looked at condition variables being used to solve the producers and consumers problem, which one of the really interesting things about these synchronization primitives, as you've seen here, we showed you two different ways to solve this safe to walk problem, one using just locks and one using the condition variable. And you've also seen producers and consumers, where you have people trying to put items in a bounded buffer and people trying to take items from a bounded buffer. You've seen that solved with two different kinds of synchronization primitives as well. And what's interesting is most synchronization problems can actually be solved by any of the available options, if you're smart enough to think about how could you do it. Now, that doesn't mean that each one is going to be equally efficient, but I mean, in a lot of cases, there are equivalently efficient solutions. So this bounded buffer problem using condition variables, this is just as efficient as the semaphore solution. Now, if you were to ask me which one would I choose for a bounded buffer problem, I'm going to pick the semaphore. Reason number one, less code. Never, ever, ever underestimate the importance of having less lines of code. Nobody wants to, if you're working in a big company and lots of people are looking at your code, which happens, you have code reviews. I mean, if you ever get an opportunity to work at Google, for the record, interesting story is you can't actually submit your code to the repo until two authoritative Googlers have actually approved of your code first. So you have to go through a lot of code reviews before you can get code actually submitted. And there's a stylistic review, which is actually a script, because that can be easily scripted, but then they actually want to look at your code. And you don't want your coworkers to have to go through hundreds of extra lines of code when there was a much simpler solution. So from my perspective, the CV solution to producers and consumers is too many lines of code. I can solve this exact same problem and the logic will be simpler and the code will be shorter with semaphores than it is with CVs. And it's just as efficient. Like there's no functional difference. They both work, but the semaphore solution is a little simpler. But when you're presented with one of these problems, it comes down to how do you think of the problem first? And if you're wondering, by the way, yes, you can solve this with locks as well. It's totally possible. Do you see this as a problem of resources or do you see this as a problem of conditions? When I look at the bounded buffer problem, the producers, consumers, I see it as a resource problem, and so I'm going to go to semaphores. But if you look at the problem and you see it as a condition problem, then you might go to condition variables. All right. Comment on Twitch about my shirt. Yes, it's cats with fish and snakes. My 2-year-old son loves it because, cats and fish and snakes. All right. So that's producers and consumers. And, if you want to challenge yourself, try to solve producers and consumers just using locks. That's a fun one. It can be done, by the way. You can do it. But you've got to think about what you're doing when you do it. It's not that bad, but it's a fun problem. Little challenge for you. All right. So I want to move on now from talking about race conditions that are caused by you. And now I want to talk about something that we have left out of the course for a really long time. And that is, we've told you to ignore the word volatile. I would like to now come back and actually talk about what volatile is and why we use it. So you've noticed, no doubt, throughout our slides, throughout OS161's code, if you've had a chance to look at it, that we have a bunch of variables are declared with the volatile keyword. And you're probably like, what does volatile mean? And then you go online, because that's, what you do these days, and you Google for volatile, and you see all kinds of arguments saying, you don't need it. Yes, you do. You don't need it. I'm going to stay out of the argument of whether it is needed or not. It is needed for OS161. I will explain to you exactly what volatile does and the consequences from the compiler's perspective. This is actually something I have a fair bit of experience with, because once upon a time I actually used to work on compiler development and optimizing and writing compiler optimizers, and the volatile keyword is actually tied into something the optimizer does. But really what we're talking about here, in order to talk about volatile, is race conditions that are happening for things that you didn't do. So all the race conditions we've dealt with so far are your fault. The next two sources of race conditions are not your fault. So the other two sources of race conditions, and again, this is really only true for modern architectures. If you go back in time, this wasn't as true. But your compiler can introduce a race condition on you. And that kind of makes sense, because you took CS350, and I taught this course, I don't know how many years ago I taught 241, but I have taught it once. And the last part of the assignment, there's, that bonus, that challenge. How few instructions can you make this code? How efficient can you make your compiled program? And it's like an account of how many instructions are used. So you understand the concept of that your compiler is going to try to optimize the assembly instructions that it outputs. And unfortunately, as part of those optimizations, you can introduce race conditions. So that kind of makes sense. The one that takes everybody by surprise is that your CPU can do it too. We think of CPUs as you fetch an instruction, you decode the instruction, you execute the instruction, you increment the program counter, and you go about your merry way. Well, CPUs are pretty smart now. CPUs these days actually look ahead at what instructions are coming down the pipeline. And a CPU will also perform its own optimizations, which means the CPU can reorder instructions to improve, generally speaking, the amount of time you're going to spend doing memory operations. Yeah. So your CPU can also introduce a race condition. Okay. So how are we going to deal with this? Because this isn't something that we did. This is something that either the compiler is doing on our behalf or the CPU did, and we really don't have a lot of control over what the CPU does. Well, the answer comes down to this concept of memory models. Because the compiler and because the CPU are performing these optimizations, they need to present to us a model that tells us how threads and how they are going to use memory. So if there's a shared region of code, they will tell us which optimizations are being performed, and they will give us opportunities to disable these optimizations so that the memory instructions will not get rearranged according to the memory models. So the memory models are telling us how memory operations can be arranged. Like, will loads be moved before stores? Under what circumstances will loads be moved before stores? Or under what circumstances will they not be rearranged? So that's what a memory model is going to do. And both, by the way, your language or your compiler will offer a memory model, but so also will your CPU. So the Sparks have a pretty well-known memory model. MIPS doesn't have one. Well, our MIPS, sorry. The MIPS 3000, you don't have to worry about rearranging your instructions in a negative way. It's too old, but newer ones absolutely did. But ours doesn't. So I want to go talk about volatile now. Volatile is related to an optimization that happens in the compiler, so this is part of the memory model for the language. So here's one of the things that has to happen. You probably know, and if you don't know, let's refresh your memory, that not every instruction is created equally. So some instructions like adds take a very small number of cycles to actually complete. But other instructions like load and store actually can take 2 and 3 times the number of cycles in order to complete. And the reason for that is when you are loading or saving a value, it's not happening on the CPU. When you load a value, the CPU actually has to send a signal along the main memory bus to the memory controller to tell it to do something. And the CPU can't actually continue until that operation has completed. So it takes more cycles for a load or a store operation to complete than an add or a subtract operation. Which means that your pipeline gets held up, waiting for that operation to complete. Now, in a pipeline architecture, we will actually end up executing the next instruction before the load or store has actually completed, which is why we need to use delay slots. So there's ways that we handle this. But the point I'm trying to make is loads and stores are very expensive. Regardless of whether you're using a pipelined or non-pipelined architecture, loads and stores are slow. So generally speaking, we want to minimize the number of loads and stores. Now, I know when you were taking 241, your optimization, you weren't necessarily thinking about optimizing how many loads and stores there were. You were just generally speaking, let's just minimize the number of instructions. But you also need to think about minimizing the number of loads and stores because they're real bottlenecks. They really slow things down. Now, we know that accessing memory stored inside a register is significantly faster than accessing memory in RAM simply because registers are actually on the CPU. So if we have, a variable that we're using right now, it makes more sense to keep the up-to-date value of that variable in a register than to have to keep going to RAM to get it, read it, update it, write it back. So there's this optimization that people perform to try to store the values of variables in registers for as long as possible. They call it the register allocation optimization. So you'll go through and analyze the code. And I've actually implemented this before, by the way. It's kind of fun to implement. But what you're trying to do is you analyze the code and you try to figure out what is the longest period of time that I can store this variable's value in a register for. And then you'll assign that variable a register. So you'll be doing this register allocation optimization. It's usually falls hand in hand with something called single static assignment, where you create a whole bunch of versions of the variable. There's a paper, I can post it if you want. And that introduces all kinds of other complications. But here's the problem. So you're trying to store the value of a variable in a register for as long as possible. So instead of the up-to-date value being in RAM, the up-to-date value is in a register, which for a function that is not multi-threaded and a non-shared variable, that's totally fine. Works great. It's a great optimization because you are going to be minimizing the number of loads and stores with respect to that variable. But here's where things get really bad. So let's suppose that you have this shared variable, shared total, and you've got two functions that use shared total. So when the optimizer goes through function A, and it does this on a per function basis, it's going to say maybe that in function A, we'll put shared total in register 8. And maybe in function B, we'll put shared total in register 3. But because the compiler was not aware that function A and function B could actually run at the same time. Oops. Who has the up-to-date value of shared total? Is it register 3 or register 8? Well, the truth is they both have garbage. So this optimization of storing the up-to-date values of a variable in a register for a long period of time really doesn't work with concurrent code. It doesn't work with multiple threads. So we need a way to tell the compiler, for this variable, do not do this optimization. Every time this variable gets used, I want you to go to RAM, get the value, put it in a register, use it, and immediately put it back. And furthermore, I don't want you to reorder the loads and stores with respect to this variable. So we want to do two things. We want to stop the register allocation on this variable, and we want to stop reordering of instructions around this variable. And the key word we use to tell the compiler not to do it is volatile. We are telling we're not stopping a race condition. This doesn't stop any race conditions in your code. All volatile does is tell the compiler, do not optimize this variable. Do not store its up-to-date value in a register. Do not rearrange the loads and stores with respect to this variable. If this variable has load, add, store, it must have load, add, store always. Don't rearrange it. Don't optimize it. So volatile is going to disable that optimization. Okay. It does. If you make a variable volatile in your code, it's not going to stop race conditions that are your fault. Volatile is only disabling an optimization that has the potential of causing race conditions outside of your hands. Volatile only disables the optimization. So in OS 161, if you have a shared variable, you should be making it volatile because this optimization is in play for us, and you do want to mark shared variables as volatile to disable it. Now, if you forget and you think, is this going to cause a problem? I have yet to see any problems caused by not making something volatile, but still, please do it. Now, volatile's use is the subject of a big debate outside of OS 161, and I'm going to let you read about that on your own and discover whether you want to or do not want to use it. But at least you know now what it does. It disables that optimization. So that's all it's doing. So there's two questions on Twitch here. Just address them both really quickly. Has reading assignment 1 been revealed? No, I should probably do that. It's about scheduling. And the second question is, when you have unified memory, does that help speed up load and store instructions since it cuts out the bottleneck of RAM? What are you referring to by unified memory? Like memory on the CPU, so stuff in caches is going to be faster than RAM. But anything that is not on the CPU is by definition going to take longer because it actually takes time to send an electrical signal down a bus. And because, yeah, it's not on the CPU. Okay, so you're referring to unified memory as memory directly on the chip, then yeah, that is faster than RAM, but you can only have so much memory on the chip, right? Like, I think, so I'm looking at my motherboard and my Threadripper machine kind of went kaput, and unfortunately the socket is no longer supported. So I'm not sure I can even replace the motherboard. I might actually have to buy a whole new Threadripper machine. But I think I was looking at them having something like 64 megs of onboard memory, which is pretty cool. That's a lot of memory on board. But it's not, in retrospect, like 64 megs may seem like a lot of onboard cache for a CPU, but that's not really that much space. You could use that up pretty quickly. I don't remember what the specs were on the new Threadrippers. And then again, I was sitting there trying to decide, do I buy a Ryzen 9, which is like a baby Threadripper, or do I go for the full Threadripper? Anyways, yeah. Memory on board is memory on chip, on die, is always going to be faster than memory that is not on the CPU itself. Simply because you have to send an electrical signal out over the bus. It takes time for an electrical signal to travel along a wire. And then you have to go to the other device. The device has to detect, A, this is for me. B, what should I do with it? Then it has to do it, and then it has to respond. So anything on board that you can do is better. But you have very limited onboard space, and the caches that are on board the CPU are only used for particular things. So, all right. So just to keep in mind, shared variables in OS 161 should be made volatile. It's just a keyword you can toss in there. It's really easy to add. The other thing is, remember, it's not going to stop race conditions in your code. All it does is disable an optimization. Okay. Now, our version of C we're using is like C89 or C99, and it didn't have a memory model back then. So it had volatile, but it didn't have a full-blown memory model. And if you look at C11 and C++, whatever C version we're on right now, I'm still kind of happy using C99. It does everything I need it to do. But new versions of languages, Java, C, C++, C#, if you actually use that, they have a memory model, and their compilers are aware that multi-threading occurs. And so the language level looking at the memory model from a language level, they have actually provided you with keywords and functions so that the compiler can know, wait a minute, this function is going to have multiple threads running through it at the same time, and the memory, it will know which optimizations are safe and not safe as a result. So in particular, if you look at C and C++ and Java, they all have like built-in locks, for example, into the actual language now, or built-in barriers, things to indicate to the compiler, hey, this code is going to have multiple threads running through it at the same time, and then the compiler will know, oh, I shouldn't do this, or it's safe to do this. But unfortunately, our version of C does not have a memory model, and all we have is the volatile keyword. That's it. So we don't have a memory model. This is, however, something I really recommend you look into. So if you are going to be going into low-level development out in industry, and you're going to be using C, C++, or even Java, you should make yourself familiar with the memory models of the language so that you know what are the appropriate functions you need to use to let the compiler know, hey, this is multi-threaded code, so it doesn't do any silly optimizations. Now, the CPU also provides us with a memory model because it's also reordering loads and stores to improve performance. And it also provides some basic assembly instructions to disable and re-enable these optimizations. They call these barrier or fence instructions. And the idea is that if you have a block of code where you want to make sure that the order of assembly as it is presented is the exact order that it is executed, i.e., please CPU don't reorder this, then you would use these barrier or fence instructions to tell the CPU, disable your optimizations now, and okay, it's safe to re-enable them again. And again, because our architecture doesn't actually have this, the R4000 does, I believe, but the R3000 does not. But modern CPUs do have these instructions, and of course this is going to work hand in hand with the memory model of the compiler and the language, because when the compiler is actually, it says, okay, this function here is a multi-threaded function, there's going to be multiple threads in here, so the CPU is, or the compiler is going to make sure it doesn't add any optimizations, and the compiler is also going to insert those barrier or fence instructions for the architecture to make sure that the CPU doesn't do anything bad either. So this stuff all has to work hand in hand. It's really interesting because I think a lot of people think you can write compilers like kind of in isolation, and OS is kind of in isolation, but actually in order to do compiler development or OS development, you kind of have to know, like, it's so tied to the architecture and the compiler and the OS, they're so tight that you kind of need to do them all together. So it's kind of interesting. All right, so I want to move on to the last topic. And this is, again, something that you caused, this is not something your compiler or your CPU is causing. This is something that's your fault. And that is the improper use of synchronization primitives can not only cause you to not solve the race condition, but it can cause another really bad thing to happen. And that's the problem of deadlock. Now, deadlock is, well, you've probably encountered it before and just never knew what was going on. So if you open up VLC and VLC does nothing and you're like, what's going on? Why is this not working? Well, it's because VLC might have encountered some deadlock and not actually been able to proceed. What is it though? So the concept of deadlock is a thread gets put into a position where it can't actually execute any instructions ever again. And there's no way to wake it up and make it execute. So let me show you a few different ways that you can actually run into deadlock. One of them, which isn't in the slides, is let's suppose that you implement lock acquire and you did not put a K assertion at the top of lock acquire to make sure that you don't already own the lock. If you don't have that K assertion at the top of lock acquire to ensure you don't already own the lock, then what can happen is that you acquire the lock and then you try to acquire it again because it's a bug in your code, and you notice, okay, the lock is occupied, therefore I have to go to sleep. So you go to sleep on the wait channel of the lock, but the owner of the lock was you. So you're asleep on a lock you own, and since you're asleep, you can't release the lock, and nobody else can release the lock because you're the owner. That's a deadlock situation. You will never make progress ever again. You are asleep forever. And there's other ways that these deadlock situations can come up, especially when we have multiple synchronization primitives because we have multiple shared variables we're trying to protect. So in the example on the slide here, we have two locks, two resources, A and B. And I have, and then they're protecting some shared variables. So here's the problem. In function A, I acquire lock A and then I acquire lock B. And then in function B, I acquire lock B and then lock A. Now this won't always cause a problem, but it can cause a problem. Here's the problem. If thread 1 acquires lock A and then gets a context switch, and function B then acquires lock B and encounters a context switch, then function A tries to acquire lock B but can't because the thread B already owns it. So function A's thread is going to fall asleep. So we have this thread over here falling asleep owning A. And so there's a context switch over here back to function B where function B then tries to acquire lock A. But since lock A is owned by function A, function B falls asleep owning lock B trying to get A. So they're both asleep, owning the resource the other one wants, and they'll never wake up. Because function B will never get woke up because it's waiting on A. And A is owned by the thread that's waiting on B. So B can't release B, and A can't release A. This is a deadlock problem. You have these two threads trying to access things in the wrong order, and they're both asleep forever. This is bad. This is bad. We don't want this. Now, a question I get asked every term is, well, can't we just have the OS know that these threads have been asleep for a really long time and have the OS just wake them up? No. Because the OS has no idea what's going on here. The OS doesn't know what you're waiting on. Oh, I mean, the OS knows which wait channel you're waiting on, but it doesn't know why you're waiting on it. And the OS has no reason to know whether or not there is a chance that you will be woken up properly. The OS doesn't keep track of what the user programs are doing. It provides the places for the threads to fall asleep, But it doesn't keep track of why they're asleep, and it doesn't keep track of if it's safe to wake them up or not. So the kernel of the operating system realistically doesn't know what's going on here and really shouldn't interfere. So you can't really solve this deadlock problem. It's kind of a problem. Now, we could solve this. You know, if we rearranged these lines of code, we could get rid of this deadlock. And in fact, since there's no magical mechanism where the operating system's kernel can detect and fix the deadlock for you, it's really up to us to write our code in such a way that these things don't happen. And there's lots of different strategies. Number one, don't acquire a lock you already own. That's pretty stupid. But there's also things like the no hold and wait strategy and the resource ordering strategy. There's also something called the banking algorithm or the banker's algorithm, which keeps track of, how many resources you currently own, how many resources are totally available, and that algorithm can also work. And I don't remember if that's taught in concurrency anymore or not, but that's a fun one. But I do want to go into talking about these two strategies we can use in our own code today that are fairly straightforward to prevent deadlock from happening in our code. So I want to start with the idea of no hold and wait. The idea is if you have a function where you would need to acquire a bunch of resources, you either get them all or you get none of them. And what that means is you can either get every resource without waiting or you can't get any. So if you have 6 resources that you need to be able to acquire all 6 without waiting. And if you have to wait on the second resource, then you have to throw the others away. What that means is while you are waiting, you can't own anything. Because that's where deadlock happens. If you are asleep waiting for something, or if you are busy waiting for something, you don't want to own any resources because you might be causing deadlock for somebody else. Now, in order to implement deadlock, or no hold and wait, we actually need something that we don't have. And that is a new function for our locks. So let's make a new page here and add some lovely grid lines. Okay. So the function that we need is called try acquire. This is not a part of OS 161. You do not need to implement it or anything like that. Try acquire is different from lock acquire. If the lock is available, then in try acquire you will acquire the lock. If, however, the lock is not available, instead of going to a sleeper, we're going to return false. So we acquire our spin lock for our lock. Now we can safely check whether the lock is available. I don't want to use owner here. Giving way too many hints for other things. If the lock is held, I release the spin lock, and instead of going to sleep, so instead of going to sleep, what I'm going to do is I return false. I was not able to get the lock, so if the lock's not available, I return false instead of going to sleep. Otherwise, we don't even need the else statement here. If the lock is available, then I say lock held equals true. Owner equals me, which is cur thread. And then I release the spin lock because I'm all done. and I return true. So there we go. This is try acquire, and we can use try acquire to implement no hold and wait. So we are not allowed to own any resources while we are waiting for something. So frustrating. Okay. So let's try to solve function A and function B here using no hold and wait. So here's what we're going to do. We are going to acquire the first lock as normal. That's okay, because if you fall asleep on this line, you don't own any resources, so it's safe. The problem is if you try to fall asleep after owning A, we would be breaking the no hold and wait. So we acquire A, and then what we do is while we are unable to acquire lock B, we are going to release A. And you could put a thread yield in here to increase the chances of context switches if you want. This is an optional this is optional. And then we reacquire A. So what we're going to do is we are busy. We're going to acquire A. When we have A, we try to acquire B. If we get B, then we jump down here into the body of our code. If we can't get B, we can't sleep while we own A, but we also can't busy wait owning A. Hence, we have to release A and then try to reacquire A again. So you either get A and B at the exact same time, or you get neither of them. You cannot sleep or busy wait while you own any resources. And then function B would do the same thing, except the two in the opposite order. This is how we use no hold and wait. Now, no hold and wait works really well. It gets a little out of hand when you've got like more than 2 resources, because then you've got to like acquire. If you had like 3, you've got to acquire the first one, and then you got to start using like go-tos and stuff, because you're going to have to try to acquire B. Once you get B, you've got to try to acquire C. If you can't get C, you have to release A and B and start all over again. So the code starts to get out of hand really quickly. But it works. So the advantage, of course, is that it implements deadlock. It solves deadlock. The downside is that you will be spinning, and that the code tends to get pretty complicated pretty quick. Okay. That's not my preference, by the way, for solving deadlock in my code. I prefer to use the second method, which is called resource ordering. Resource ordering does not require any special functions at all. You can just use the functions you have right now. And what you're going to do is simply assign every resource in the system, a number, a unique number. And then you make sure that you always request resources in a strictly increasing order. So it's on you to remember the order and make sure you're acquiring in the right order. But if you do this, you end up with no deadlock. And let me actually give you a demonstration of this one here. So we'll solve the problem on the previous slide using resource ordering. Let's use, red, I guess. So let's say we've got, so for function A, and we have 2 locks. We've got lock A and lock B. And I'm going to assume, just for the sake of discussion, that A is resource 1 and B is resource 2. And then I've got function B. And let's say that it was passed this. So remember, B is resource number 2 and A is resource number 1. So what I'm going to do is, because I know that those are the resource numbers, then in my functions, all I have to do is make sure that I acquire these resources in a strictly increasing manner. So A before B. So if I do that in both of these functions, always acquire in a strictly increasing order, no deadlock. Hold on. That's it. No deadlock. Because if I get A and there's a context switch, then the other thread is going to try to acquire A, fall asleep because it can't get it. So then I manage to successfully get B, and then I can enter my critical section, do what I need to do, release A and B, and then function B can go and get them both. So no deadlock. Now this can get a little bit out of hand as well. I hate that I have to keep restarting this. It's really annoying. So this is where you end up with a problem. Let's say that you have a bunch of resources. So some function here. Let's say it takes parameters X, Y, and Z. But you don't know that X, Y, and Z. You don't know what resource ordering there are. You would have to, with resource ordering, sort by resource number. So you don't need any special functions, but you are going to need to make sure that you are sorting the resources before you actually acquire them. And of course, comparative sort has a best case runtime of n log, or it's big O of n log n. So yeah, there's side effects. Neither one is perfect, but I certainly prefer the resource ordering one because it is a bit more straightforward. There's no special functions. And generally speaking, when you have a problem like this, you don't usually have a lot of resources to acquire. Okay, so we've still got a little bit of time here. So what I would like to do, I apologize here, I have been running some code on something like 41,000 movie scripts. So my computer's a little bit angry with me today. So if you go into the handouts zip file that is posted on Piazza, you will find a problem called Q transfer, where X refers to transfer. And this is another old problem from a previous midterm. And what it wants you to do is to solve the following synchronization problem and make sure you have no deadlock. Deadlock bad. So we have a multi-threaded program with n queues of items. And those are shared queues. And we need to support a function called transfer. And the idea of transfer is we want to take an item from the ith queue and put it onto the jth queue. So we're going to take an item from one queue and we're going to put it onto another queue. And the idea is that we want to be able to run transfer concurrently. I don't want one transfer operation to happen at a time. I actually want this to be able to run concurrently. So using locks alone, how could I solve this problem? How many locks do I need to solve the problem? And what's the best I can do? How many possible transfer operations can I have running at the same time? So what is the most? So let's look at some possible solutions for this. Again, that's the Q transfer problem, and that's posted in that Piazza thread. Okay, so let's start by looking at the simplest solution. The simplest solution is to have a single lock. One lock. And what we're going to do is simply inside of transfer. Now, don't worry about the actual transferring code. We are going to acquire the one lock, do our bit, and then release the lock. So, have we solved a race condition? Yes, you have. There's no race condition now. You can only perform one transfer at a time. Great. Is there deadlock? No deadlock, because there's only one lock. Is this a good solution? No, it is not a good solution. The maximum number of transfers that can happen at any one time is 1. So there was absolutely no point in using multiple threads at all. Nope. Bad idea. Solution 1. Nope. Here is another solution. Let's use no hold and wait. 1 lock per queue. Let's suppose that each queue has its own lock. So what we would do inside of transfer is we would acquire the lock for Q1. And well, let's say this, so we've got Q1 and Q2 here. Not necessarily in a sorted order, by the way. And then, we would do the while cannot to acquire the lock for Q2. We're going to release. And that's supposed to be a Q, by the way. Okay. And then down here, we go about our business, and then we release them. So that's another solution. So, is there a race condition? No race condition. Everything is fully protected. Is there deadlock? No. No deadlock because we've used no hold and wait to guarantee that there would be no deadlocks. Can we have multiple transfer operations happening at the same time? Yes. Yes, we can. How many? Well, if we have n queues and we are transferring from one queue to a different queue such that the queues are different, then the maximum number of transfers that can happen at the same time here is actually n over 2, because that's how many unique pairs of queues there would actually be, where, you're taking it and removing it from the set each time. Okay. Are there any other solutions? Absolutely. Instead of solution 2 being no hold and wait, we could actually do the resource ordering. The resource ordering method, we would have to check whether Q1's resource is the lower one than Q2, because the Q1 and Q2, even though we've labeled them such, that doesn't mean that we could be doing a transfer between 5 and 1. And 1 and 5, and we need to make sure that, so we would have to check for resource ordering. So for resource ordering, the solution would look a little different. So this is solution 3. Again, 1 lock per queue. So what we would have to do in transfer from Q1 to Q2 is we would have to check if Q1.num, now the number is the resource number, is less than Q2.num, then you acquire Q1, and then you acquire Q2, because you got to sort them first, remember. Otherwise, we acquire Q2 and then acquire Q1. Okay, so that's how you solve it with resource ordering. Again, the maximum number of transfers that can happen at once is going to be n over 2, because that's how many pairs we can actually make from n different queues. Are there other solutions? Yes, there may be other solutions. I have a lot of students ask me, well, what if I put the values from Q1 and Q2 into temporary variables and then push them back on again? That technically works, but the problem that you end up there is that if order matters of these operations, you end up with things out of order. So it's not really a good solution. You really do want to own the lock on the queue for the entire duration of the transfer operation. So you want to make sure that those two queues are frozen in time at the point of the transfer and nobody else can touch them during the transfer itself. Because otherwise you could have somebody playing around with the queue and then you get all the items on the queue in the wrong order. All right, so there's 3 different solutions. Now, if we were grading this on a midterm, The first solution might get 1 mark out of like 8 or 4, simply because you didn't have deadlock and technically speaking you didn't have a race condition. But only the no hold and wait or resource ordering solutions would actually get full marks because they actually support the maximum amount of concurrent threads running at the same time. And when we've had questions like this on midterms before, people forget to sort. And if you don't sort for the resource ordering, then you would lose a couple marks probably. But of course, you're not actually going to be writing a midterm in the pack. So this probably doesn't have any impact on you. But hey, you know, it's good to remember what life used to be like eons ago. I mean, you know, you're sitting there, you're like, oh, I haven't been on campus in like a year and a half. It's like, I haven't been in my office in a year and a half. Like, do I have like a juice box from one of my kids sitting on the desk? This could be so gross. Pretty sure I don't. I keep my office pretty clean, but yeah. The amount of dust that's going to be on my TV in my office is going to be huge when I ever actually finally get to go back to campus. Hopefully soon. All right, so that's it for today, and that's also it for talking about synchronization. In our next episode, which will be Tuesday of next week, we are going to start a new topic, which is processes. And so our entire week next week will be completely dedicated to talking about lovely, lovely processes. And we will get to see how threads play a role in processes. We will get to see how user programs are able to actually cause the kernel to do things. And after next week, you should be able to do assignment 2. And we will be having a whole episode dedicated to how to do assignment 2, just like we will be having a whole episode dedicated to how to do assignment 3. And if you like to look ahead, you're welcome to look at our previous terms playlists and watch those videos, of course. And there are many, many videos going back to even when things were not in online. Sorry if you heard that big bang. I actually have a bunch of heavy bags downstairs, and I think one of them just got kicked, and it kind of shakes the whole house because it's hanging from the floor joist. All right, so we will see you Tuesday of next week to talk about processes. I hope you all have a lovely weekend. It's supposed to be pretty hot, so go outside, but bring lots of water. Yeah, we'll see you then next week.